When doing an outdoor link, you need to keep in mind that there's this thing called a Fresnel zone. The Fresnel zone, it's French, so it looks like that. It's pronounced Fresnel. The Fresnel zone is an elliptical shape of signal. Signal does not travel in just a straight, perfect laser line like you would think. It actually has kind of a curve to it. So we could actually see that here. You'd actually see this curve of signal. Now from the end, if we could look at this on the end, we have in the middle what we call a point source. And then we have multiple Fresnel zones, like this may be called 1FZ, the first Fresnel zone. That is what we're worried about. You can't block too much of the first Fresnel zone. This center point source, if I can see one antenna from the other, maybe I'm standing on this building, I can see the other antenna, that does not guarantee success. That's called a visual line of sight. I can see from one point to the other. But then there's what's called radio line of sight. And that is, I can't block too much of this first Fresnel zone. In fact, the magic number is 60% of the first Fresnel zone needs to be open. So your question is, how do you decide that? Well, let's say we're going to do this link. We need to first make sure, is this link even possible without Fresnel zone encroachment? So we have to do some calculations. Now, we're not going to go through the math of how to calculate Fresnel zone. This isn't a math class. Online, just type in Fresnel zone calculator. The first link tends to work well for me. Go to that link. You type in your distance. We have 8 miles. Your frequency. We're going to start this calculation at 2.4 gigahertz. So we have a 2.4 gigahertz link, and it will tell us our first Fresnel zone. Now, given this, the calculator came back and said the radius of our first Fresnel zone is 52 feet. Now, keep in mind, this is a circle. We are looking at an urban environment here. So if we saw a building, maybe we have a building like this, and that building, let's say, is 48 feet tall. So, do we have successful system? Can we do this link? Well, yeah. We have left the 60% of the first Fresnel zone open. Our building is not encroaching on that, so this is successful. It's pretty simple, except for one thing. This is going to be news to some of you, and I hate to be the one the bearer of this news, but the Earth is round. It's not flat. So if we're 8 miles away, even though the elevation here, let's say the elevation is 100 feet of elevation, and over here, it's 100 feet, and we'll say it's perfectly flat. Everywhere we measure is 100 feet of elevation. There is still a curve, right? That's not quite to scale, but there's still a curve to the Earth. In fact, at this 4-mile point right here, right in the middle, it's actually about 10 feet. We have what's called a 10-foot earth bulge that we have to account for. Oh, goodness, what do we do now? Now we have first Fresnel zone encroachment. Is this link dead? Well, at 2.4 gigahertz it is. We could not do this link successfully at 2.4 gig. So what can we do? Fresnel zone is frequency dependent. The cool thing is, at higher frequencies, the Fresnel zone gets smaller. It's part of the reason that point-to-point links like this are typically in higher frequency. In fact, a point-to-point link in 2.4 gigahertz is virtually unheard of. You're really not going to ever do that, so please don't. Every outdoor Wi-Fi product that's point-to-point is 5 gigahertz. So will this solve our problem? Now, due to some scaling constraints here, let me change this a bit. So we are encroaching here. Now, if we change this to 5 gigahertz, 5 gigahertz, our first Fresnel zone now is 33 feet. So we've gone from 52, where we were before, to 33 feet. So 48 plus 10 plus 33, that's 58. That's less than 100. So what that means is, at 5 gigahertz, even accounting for the curve of the Earth, at 5 gigahertz, we now have a successful link. One of the things to keep in mind about this, we learned about antennas and beam widths. Fresnel zone has nothing to do with that. I know that sounds weird, but an antenna cannot change the Fresnel zone. I don't care if you're using high beam width, narrow beam width antennas, or you're using omnidirectionals. This Fresnel zone is created between the transmitter and the receiver, and it does not change with antenna type. That can be tricky. So you've decided you're going to use a 5 gigahertz link. You've taken into account the curve of the Earth. Your building is still going to go over your building. You now have the makings of a successful link. Fresnel zone indoors, we don't worry about it. You're like, well, how can it even work through walls? Indoors, Fresnel zone doesn't come into play. We never talk about it. We never use it. Outdoors, very much so. In fact, this is the first step. If a customer comes to me and says, all right, GT, I need to do this link, the first thing I'm doing is a Fresnel zone calculation. I'm making sure that we can actually achieve this link given the obstacles that are in play. Again, keep in mind, in an urban environment, it may not be a building at the bottom of the link. It may be a building off to the side. Again, it's hard to draw that three-dimensionally here. But always keep in mind you need to keep that 60% of the first Fresnel zone open. What we're going to do next is a link budget. Once you know that you have clearance, you need to know what kind of transmitter, antenna, how much loss do I have across the air, what's the receive sensitivity of my receiver. And that way we can find out what components we need for a successful outdoor link.